For longitudinal pulses, we're going to deal mainly with the most common type, namely sound. When I go, ha, that pulse propagates across the room. What determines how quickly it gets from this side of the room to that side of the room? What should matter? What should determine how quickly it moves? The density of the air? Okay. So let me write this down. Density. What else?
Any attractive forces in the fluid that you're...
Okay, we're going to assume that it's going through air and that the air is an ideal gas, so we're going to take that simplifying limit, but you're right. Other, raise your hand please, because I'm deaf.
Temperature.
Temperature. What else?
The force exerted by your voice? The initial force exerted by your voice?
The forces of...
The initial force.
Oh, the initial force with which you... Ha! Also the initial conditions. Initial conditions.
That would affect how far it goes, but not the speed.
Okay, we'll come back to that. Pat?
Other longitudinal forces.
Other longitudinal forces?
Like pulses. Like if you shouted, he shouted.
Oh, whether there's two going on at once. Okay.
Not like reflective, like a wall.
Whether it reflects off. Okay, let's just take the simple case where there's one pulse and it's traveling in a straight line across the room.
The amount of particles, I guess.
The number of particles in the room?
Yeah.
Okay. That would be the density of how tightly they're packed.
Sorry, I missed that part.
Okay. Have you ever breathed in helium and then you talk like Mickey Mouse? That is because sound travels at a different speed through helium than it does through air, which is mostly nitrogen. And the difference is that helium is lighter. And so it turns out that the mass of the particle matters. It turns out what we find is that sound travels across the room as fast as the particles can travel. Okay? In order for this gossip to get across town, I got to take it to my neighbor, she's got to take it to her neighbor, and it has everything to do with how fast we can run and get to our neighbor. Now, it does not depend on density. I thought it should, but it doesn't. Let me see if I can explain why. Suppose we have a relay race. There's the start, there's the finish, and this relay race is between two relay teams, Bozeman and Belgrade. Bozeman has a large track team, and so they've got a lot of runners. And they just run and hand off the baton. Belgrade, not so many runners. Okay? But if we make the assumption that all the runners on both teams have the same average speed, this race is going to be a tie. Because no matter who's running, they're running at the same rate. And by the time this runner passes off the baton to the second runner, this runner has already passed that baton and already is passing that baton. And then this one goes and passes the baton, but in that same time, they've got the baton here, and they cross the finish line together. There will be more collisions, more passings of the baton with higher density, but the disturbance, the sound, doesn't get to the end of the row any faster than you can travel. Okay? And so what it depends on is how quickly the particles move. And we find that that's dependent on the temperature and the mass. Now, in air, mostly nitrogen, sound travels at 343 meters per second at room temperature, which is about 20 degrees Celsius. And we find that as the room heats up, it goes a little faster. 0.6 meters per second for each 1 degree Celsius that we heat up the room. And if we cool down the room, it goes a little slower. Now, the formula that we'll never use and will not be on the front page of the exam is this value here, this formula here, where this is the temperature in Kelvin, the absolute temperature in Kelvin. This is the mass of the particle in kilograms. And this K value here is not, I repeat, not the spring constant. This is Boltzmann's constant. It's a number that you're not going to have to use, so I'm not going to belabor you with it.